kind of catch up to you guys a bit here. So this is primarily a product rule, right? So you'll get 3 comes down, and then the 2 comes down off of this guy. Thankfully, the inside's not making a chain rule, right? Just nice slopes of 1 inside. It's nice. So then what can come out? We'll take 2x minus 1's out, and 1x plus 2 out. Leaves me with 3x plus 6 plus 2x minus 2. And that's where my 5x plus 4 comes from. Okay. We've done that problem a lot. So hopefully it's that third dude. You can't just forget about it. It's going to give you another critical number. What are my critical numbers then for the first derivative? Sweet. Like it. So I got -2, -4/5, and 1. Well, I gave myself such a small number line, but oh well. Multiplicity is just, not only is it a cool word and a good movie, but it's really flippin' useful. Why does it work? Is this ever going to be negative? Is this term ever going to be negative? No. So it's not going to contribute to a change in sign. That's why it doesn't change sign around 1. But what's this do? On one side of 2 it's positive, on the other side of 2 it's negative. So it's going to change the sign of the whole thing. That's why multiplicity works. So if I plug in 18 billion, or 2, I'll get positive, 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 so it's positive. Multiplicity is even, stays positive. Odd everywhere else, changes, done. Yay, less work to do. Or you can plug in a number from every region, that'll still work. Just take it longer than it should. So it's increasing in a lot of places. -3, -2, -4/5 to 1, and 1 to infinity. Why can't I just say -4/5 to infinity? Because it's 0 at 1. It's not positive at 1. It's not increasing at 1. It's resting at 1. And where is it decreasing? -2, -4/5. I like it. I don't know why I gave myself so little room here, but oh well. What's true at -2 then? So -2 is the location of a max. Goes up, comes down. There's a max at -2 comma something or other. How do I figure out that something or other? Plug it into the original. So -2 minus 1 is -3 cubed is -27 times 0. I should have probably started there. You get 0. Well, what's the min? Happens at -4/5. Is that cool? Goes down to it, goes up from it. That must be a minimum then. And then when you plug it, I don't know what the shit. What do you get when you put -4/5? -8.4, roughly. Okay. Remember, you can round to 1 decimal place. We're doing this by hand, so you have to be more precise than that. I don't care who you are. All right. Have you guys all got to the second derivative yet? A few of you guys were just getting there. So how would I do that second derivative? I would start with the results of this guy. This is going to be yummy. It's got 1, 2, 3 parts. Let me write down f prime first, so I got it right here. So f double prime. See if we can do this Derivative of this, leave the other two alone, and so forth. So I'm going to have 3 parts because I have 3 factors. Makes sense? Right? 1, 2, 3. So if I do the first guy, leave the other guys alone, plus, let me just go this way. Leave the first guy alone. What's the derivative of the middle guy? 1. Leave the last guy alone. Plus, leave the first guy alone. Leave the middle guy alone. What's the derivative of the last guy? 5. I love it. Mm-hmm. What comes out of all those? Only x minus 1. And that kind of sucks. So what am I left with? 2 times, let's see, 5x squared plus 4x plus 10x plus 14x plus 8. Oops. Is that cool? Took an x minus 1 out, so it's 2 times this. Plus x minus 1 times 5x plus 4, because I'm taking one of those out. So it would be 5x squared minus 5x plus 4, so minus x minus 4 plus, let me write this for myself, 5x plus 10, x minus 1. So that's going to be 5x squared plus 10 minus 5 minus 10. Oh my God. Okay, now it's just a bunch of like terms to put together on the inside. So you get x minus 1. Oh my God. Let's see. 10, 15, 20, 28, 27, 32. I don't remember what the answer is supposed to be. 16, 12, 2, right? That looks good. So that's x minus 1. Take a 2 out. 10x squared plus 16x plus 1, which sounds familiar. Woo! Was that quick? Not that quick, no. Was it hard? Oh, hell no, it was not hard at all. I'm not just talking about for me. It should also be for you. Not a big deal. It's a bunch of foiling and like terms. Ooh. Here, I'll do half of this one. 1. What's the other critical numbers? Well, I did 1/3 of it. How do you get the other critical numbers for E? Quadratic formula? Yes, because you can't factor this thing, right? Not easily. So, how does quadratic formula work? Negative b. No. Negative b.
Yeah, negative b. Square root of.
Plus or minus.
Plus or minus square root.
Square root of. B squared.
Minus 4ac.
What is b squared?
256.
Minus 4ab, so minus 40, all over 2a. I like it. So that's negative 16, give or take, square root of 216 all over 20. And then you can just plug in the calculator and get your 2 things. That's fine. You can simplify the radical, but at this point we just need to get decimal approximations. So what are you going to do? Negative 16 plus rad 216 over 20. This is where some people just kind of tune out. All right, so this isn't 4. The answer isn't 4, but it's still a number. I'm still going to put it on the number line. I'm just going to do the same stuff. Just it takes a little bit longer to get it than it did to get 1. Who cares? It's the same thing. It's just a slightly more interesting number. What do you guys get? I'm sorry. Negative 0.06?
So,
Does that make sense? Yeah, roughly. Well, it seems like it should be a little bigger.
or that's just a negative 1.5. Pick one of those two.
No, you're right. Negative 0.06. Negative 0.07 really, but yeah, you got it. Okay. And then negative 16 minus rad 216 over 20. Negative what now?
1.5.
1.5. I like it. And sometimes we do some stuff and then we forget what the hell we just did. What are those two things? Two more critical points. I like two more critical numbers. So we got x equals 1, x equals negative 0.07, and x approximately negative 1.5. So we got negative 1.5, negative 0.07, and 1. Can somebody tell me what their each multiplicity is? Each of them? This is multiplicity 1. This we broke in half, so they would each be multiplicity 1. So everybody's got odd multiplicity. Sign's going to change everywhere. So I always start with the positive stuff if I can't. Well, here's zeros in here, right? So if I put a 0 in, I get negative times positive. So I get negative. Let's just double check. If I put an 18 in there, I get positive times positive. It's good. That looks good. It changes sign everywhere. Is that? Because multiplicity is odd everywhere. How many inflection points do I end up with? 3. Because it changes sign around this, around that, and around that. Holy shit, they're all inflection points. This is going to be a funky graph. So let's see. What's this mean right here by itself?
Concave down.
Concave down. So sad, happy. Sad, happy. Or, good position for a cup. Bad position for a cup. Holds water, doesn't hold water. I've heard that too. So my inflection points are at negative 1.5 comma something, negative 0.07 comma something, and 1 comma 0. So that one's not let me know the calculator. Alright, so maybe now I've gotten ahead of everybody almost. I wanted to catch up to you before you really started to graph because I want to show you one more thing about at inflection points, what to do to really make it make sense. So Adam, what do you get when you plug a negative 1.5 in? See you got that?
Negative 3.9.
Negative 3.9? What about negative 0.07?
Negative 4.6.
Neato. Okay. So now we can graph this thing. Take this away. Yeah, we don't need this anymore. Okay. What are my x-intercepts? Good Lord, Jeff. You just see them, right? What are the x-intercepts? 1, 0, and negative 2, 0. You gotta like problems that start off factor because this intercept stuff is easy. What about y-intercept? How do you find the y-intercept? You make x.
You make x 0.
0. So you get negative 1 times 4. Everybody cool with that? Okay, 2 of you. Okay, 3. Oh. And I think that's all the extra stuff I asked for. And then now I got to figure out what scale makes sense. So for my x-axis, the scale that makes sense seems to be, a nice scale. Where are things happening? Look, negative 2, negative 4/5. These are all less than 2 stuff, So it looks like maybe I can go out to 2 on both sides. Does it make? Do you guys see what I'm saying? I mean, if I had if this was 20 comma something, then on x-axis scale, it's probably going to have to be different than 1. Okay, I like it. What's the scale of 1 seems to make sense here. What about the y-axis? So look, see, that's my most extreme output, right? So I heard somebody say 2's, maybe by 2's makes sense. Got to go down to negative 8.4, and I got to go up. Do I have to go up at all? Everything's down, isn't it? Yeah. There's this stuff. These are all down. All right. Everything's happening down here. So up here, I don't care. Oh. Sorry. So if I really would have been smart, I would have just not even done the top. I would have put this here. Everything would have been underneath, but oh well. Okay. So now I plot all my anchor points. And I label them as to what they are, because that's going to tell me what to do as I hit them. So what do we got? We got intercepts. 1, 0, negative 2, 0. 0, negative 4. Maybe I should do this in a different color. What else do I got? I got max and min. Negative 2, 0 is a max. Negative 4/5, negative 8.4 is a min. How are we doing so far? You guys all right? If you label them as you plot them, graphing becomes super easy. Or, easier. Anything else? My inflection points. Negative 1.5, negative 3.9, negative 0.07, negative 4.6. Oh, this is yummy. Now, what are those? I didn't label. It's my fault. Those were inflection points. Okay. Let's try to do this now. All I need is to get started. It should be increasing, which makes sense because at negative 2 it's a max. Increasing, and it should start off concave down. And you see how that makes sense? Look, see, doesn't I want to do this? I don't know, you guys. If you wanted to, you could put in negative 3. You could plug a negative 3 into the function and see where it is. You can get one more anchor point, but I know it's concave down and increasing. That seems to go along with what it's doing here. It's concave down, increasing. Max, so it turns. What happens right here? Make sure this is really clear. Now it becomes concave up. So now you just start, and it's supposed to get over to here, right? There's a min. Concave up now. Oh, Jeff, you can do it. And what happens right here? Concave down. And what's the next thing it's supposed to get to? Did I forget a max? No. Did I forget an inflection point? Yes. 1, 0 is an inflection point. There you go. Well, so make sure you label every point. It's probably a good idea. So what's going to happen? Now it's going to become concave down. This is where it gets a little bit freaky, but what you can do for yourself is start here. It's concave down. It's because that point really should be closer to the y-axis. Oh, concave down. And what happens here?
Concave up.
Concave up, and it's still increasing. That's just an inflection point, not a max. So now it's concave up. And if you graph that in the calculator, you should get that same shape. Woo! Where's the other side? Oh yeah, the other side's super yummy. Here, let's do this. Let's take a break from that idea for a minute. Let me talk about L'Hopital's rule. We'll do this. This one we'll do. That phrase, whenever I say next time, part of your brain goes, pack up, go. We'll do that so next time. We'll do L'Hopital's rule right now. We'll do that one next time, and then we'll do, I don't think we're going to make it all the way through chapter 4, which makes sense, because we didn't make it through all the way through chapter 3 last time. So we're like a couple sections behind. So we got what they want from this here? Yeah. Now let me start off by reminding you what happened in section 310. That actually is going to connect somehow to section 4.4. And actually, let me start off with motivation for 4.4. Now, normally, if we have polynomial ratios, we can just divide by the highest power and do that kind of stuff, right? But can you do that here? Often I get people that tell me this, and they start using this everywhere. What? Is this true? If this was true, why would we have this function if it's just this function instead? That's kind of stupid, right? That's one reason why I hate radicals, because it's not different from a fractional power. They're the same. Why do I have two different? Anyway, so what they mean is this, so be careful, right?
Right.
So I can't just rewrite ln as 1 over x everywhere I see it. No, it's the derivative. We currently do not have a way to do this besides making a table of values or plugging in the calculator, some big-ass numbers, right? I want some way to do this by hand. Somebody's like, that's you, man, but that's also you. So here, let me bring back in something, recall from 310. Remember that? What equation is this really? It's just y1 mx minus x1. That's a stupid equation. It's just tangent lines. So that's one reason why I hate that to make 310 a whole separate thing, is just find an equation of a tangent line. Okay? So this is of the form well, let me start off with this. Let's say it's easier if I look at this instead. This is our get out of there, B. If the limit of the top is 0 and the limit of the bottom is 0, isn't that an indeterminate form? Remember that? Mm-hmm. And did that mean you stopped there?
No.
No, that meant you had more work to do, right? Well, I'll show you how it relates to this problem in a minute, but let's start with this because this is an easier one to talk about. So if I'm looking at this, watch what I can do. Look what I can do. Let me replace this with what it is approximately, because where is this approximation actually exact? Where is this exactly true? At x equal to, who remembers? What is A? What is A? So if I say find the tangent line for square root of x at A equal to 4, then that means the tangent line will exactly equal square root of the thing at 4. So A is the point where this works perfectly, this thing. So what is f of x approximately? It's approximately f of A plus f prime of A times x minus A, right? And what's g of x? It's approximately g of A plus g prime of A times x minus A. So notice, this only works if f and g are both differential at A. Okay, I want to get this. All right, this. Let me write that in a little bit different form. Those of you that know L'Hopital's rule, you're like, why is he making it so hard? Because this is explaining why it works. And then the actual rule is stupid easy. Let me rewrite what I've got so far. Let me write this in a slightly better way. This is basically m1 times x minus a plus b over b1, m2 times x minus a plus b2. Is that cool, you guys? You see what m1 is? M1 is that, m2 is that, b1, b2. Okay. What is this limit? We know what this limit is. What's the limit of 3x plus 7 over 4x minus 2? Yeah, m1 over m2, which was f prime at a and f and g prime at a. So it's the ratio of those two. It's kind of cool. So what does that mean? So this is why this works. What does that mean, nuts and bolts for me? What that means is, if something is an indeterminate form, and this, of course, is infinity over infinity, which is indeterminate. Is that cool? As long as it's in indeterminate form, I'm allowed, what that means is the limit of these functions is equal to, I always put a little LH to tell myself I'm using L'Hopital's, is equal to the limit of the ratio of the derivatives. What's the derivative of ln of x? And what's the derivative of x minus 1? 1. And what's the limit as x goes to infinity of 1 over x? The limit as x goes to infinity of 1 over x?
0.
0. Over 1, sure, which is 0. Remember this one? Is that indeterminate? Is it indeterminate? When you plug a 0 in, what do you get?
1. No, wait. You get 0 there. And
0 over 0.
Right.
That's indeterminate, so am I allowed to use L'Hopital's? Yes. So this becomes using L'Hopital's. I always put a little LH to tell myself what the shit I did. Because sine x does not equal cosine x, but the derivative using L'Hopital's. Notice I am not doing quotient rule or something. The rule is the ratio of two functions limit is the limit of the ratio of the derivatives. So derivative of the top, derivative of the bottom, which some of you guys do already when you should be doing quotient rule, but you just got ready for this early. What's the derivative of sine x? I just told you. What's the derivative of x?
1.
1. And when x goes to 0, what's cosine x do?
1.
Goes to 1. Nifty. All right. And one last one here. What you got, Jeff? Yeah. Let's just do infinity. I want to show you an example of multi-step problem. This one's really going to be yummy. All right. Is this indeterminate? What form is it in? If you let x go to infinity, it's in the form what? When x gets really, really big, e to the x squared gets really, really big. Big's cubed is big. All right, is that indeterminate? Yes. Okay. I think I'm definitely going to stop after this because you guys are brain fried. So then using L'Hopital's, I'm allowed to use L'Hopital's because it's indeterminate. What's the derivative of e to the x squared? 2x, e to the x squared. I like it. Derivative of x cubed? What can I do to this? Now this isn't L'Hopital's or anything. This is just simplifying what I'm looking at. What happens? and x cancels. Is that cool?
Mm-hmm.
So I get 2 e to the x squared over 3x. Is that determinate yet? No, when you plug infinity or infinity. Can I use L'Hopital's? Yes. So you don't just keep using L'Hopital's until you get a number. You got to stop when it's not indeterminate for 2 reasons. L'Hopital's only works if it's indeterminate. The second reason is more basic. If it's not indeterminate, that means it's determinate. Stop and determine the answer. Right? That's why I love the word indeterminate. When it isn't that anymore, that means you should stop because you can determine what the hell the answer is. So what, if I use L'Hopital's one more time, what happens?
You get 4x e to the x squared
Good.
over
4x e to the x squared over
3.
3. Is this indeterminate still?
No.
When I plug infinity, when I let x get really, really big.
You get 0. I think, wait.
The top gets really, really big, and the bottom is 3. So really big divided by 3 is really big. Woo! That's section 4.4 is L'Hopital's rule. It makes, if you look back at a lot of the limits we did before, this is where some of you that knew it were like, I can't use it? I'm like, of course you can't use it, shit. Now you can use it. So any limits you got to take, if it's indeterminate form, you can use L'Hopital's. That's awesome. Okay. That's enough. So I think what's going to happen, next time I'm going to do that quiz first. Make sure everybody sees that. Including me when I look back at this to remember what it was on. And then we're probably going to do 4.7. And we might try to do 4.8. We'll see how much time there is next time. So after next time, we'll know what the test is going to cover.